lesson 7-8 here, we're going to look at inverse functions and inverse relations. And we're actually going to do relations first. Recall that a relation is a set of ordered pairs. If we look at this example, the ordered pairs of the relation 1, 3, 6, 3, 6, 0, 1, 0. So notice they're in set braces. It's a set of ordered pairs. They're the coordinates of the vertices of a rectangle. Find the inverse of this relation and determine whether the resulting ordered pairs are also the coordinates of the vertices of a rectangle. Alright, and then down at the bottom here, let's look at this. Finding inverses. The inverse relation is the set of ordered pairs obtained by reversing the coordinates of each original ordered pair. And that's very key. You're going to switch the x and y. So in other words, the domain x becomes the range, and the range becomes the domain. Because domain and range end up switching because we're switching x and y. So the inverse. Let's just write it down here. The inverse set of relations. We'll put it inside set braces. So notice my first point here is 1, 3. So you're going to switch x and y. So that's really what we're doing here. Switch x and y. Switch the domain and range values. The next one we have 6, 3. That becomes 3, 6. Then we have 6, 0. That becomes 0, 6. And then we have 1, 0. That becomes 0, 1. So there is the inverse relation. Now what we're going to do is I will graph the original in black. So let's graph the original relation. So 1, 3 is going to be right there. 6, 3 is right there. 6, 0 is there. And 1, 0. So I'm going to draw the original in as a rectangle here. They told us it was a rectangle. So there's what we have. There's the original. Now let's graph the inverse. Because I wrote it in red, I'll graph that in red. So we're going to plot 3, 1. So that becomes right there. 3, 6 is right there. And then 0, 6 right there, and 0, 1. So here is, I'll draw this one in solid. There's my inverse relation. So it asked us, determine whether the resulting ordered pairs are also the coordinates of the vertices of a rectangle. Yes, the inverse is also a rectangle. And what you want to notice with inverse, every graph, inverses, if you look at the original and the inverse, okay, the original, in this case figure, a rectangle, and the inverse are reflections over the line y equals x. Now remember the line y equals x, and I'll draw this in green. That is basically the identity line. It's like 1 over 1x is the slope plus 0. So that basically, and for all this stuff we do with inverses here, we're going to reflect over this line. Okay? Now, in this case, both the original and the inverse have some parts on either side, but you can see if you reflect that over, the half that's below it and flip it up, and then the half, the little corner that's above, flip it down, that's reflected. All inverses, whether they're relations or whether they're functions, are reflected over the line y equals x, and that's very key, and I would like you to draw that in, and we'll take a look at some examples here. So for instance, here, now this one you got the blue triangle, right triangle down below. There's the line y equals x. So you can see that these 2 points right here would end up, this point would end up being up there, and then this point would end up being up there. Okay, and then you would connect them, but they're reflected over that line y equals x. Alright, and then we get to functions. Now remember, always, and we've talked about this many times, that f of x, that means y. So f of x is y. So when you're given a function, here's what you want to do. You want to find the inverse, so we're going to switch x and y, then solve for y. That's how you find the inverse function. So I'm going to put down that this original, we're going to make this a y, so it's y equals negative 1/2 x plus 1. I'm actually going to, now part B is asking us to graph it, but let's graph the original f of x. So that's in slope-intercept form. Y-intercept is 1. Slope is down 1, right 2, so down 1, right 2, down 1, right 2. We'd be right here. Up 1, left 2, going this way. So my line's going to look like that. And let me actually grab a line here. Let's grab this one. So we're going to look like that. I'm off a little bit there, but there's my original. And I'm going to call that my original f of x. Now we're going to find the inverse. So we switch x and y. So what happens is we make, this was a y right here. Oops. Let's undo that. Go back to that. This was the original y. That was x. So we're going to make this x, and we're going to make this y plus 1. Now we're going to solve for y. Well, if I'm going to solve for y, I got to get y alone. My next step is to minus 1. So I have x minus 1 is equal to negative 1/2 y. Now, you can't really divide by a fraction. You have to know the rule that I'm going to multiply by the reciprocal of this fraction. So I am going to multiply times negative 2 over 1. That's the reciprocal of negative half. So I'm going to multiply by negative 2 over 1, which really is just negative 2. So I'm going to take that off of there, and we're really just going to multiply by negative 2. If I do that, I'm going to distribute my negative 2. So it's negative 2x plus 2. And I'm going to rewrite that with my y on the left side. So negative 2x plus 2. There is the inverse. And here's the notation that we use for inverse. We're going to go and switch this back to inverse. So we go f negative 1 of x. Looks like an exponent of negative 1 is negative 2x plus 2. And you could leave it as y, and then just indicate it's the inverse when you graph it, but I think it's best to write it with the inverse notation, which is this. Now we're going to graph this. So my y, this is a line in slope-intercept form. So positive 2. My slope is negative 2 over 1, so I'm going to go down 2, right 1, down 2, right 1, down 2, right 1, and so on. If I went the other way, I'm up here. Let's go ahead and draw the line. So let's draw the line here. And let's label this the inverse of x. Now these are reflections over the line y equals x, which basically is this line right here. So you've got the line going on both sides, but draw in the reflection line. But that would be, each half would be reflected up to the other half, and you get the line going on either side. Okay, but that's the line y equals x, and when you do your problems, I would like and you can put that in there before you graph either one too. Alright, so here would be an example of a couple inverses. Now let's just take a look at this one. Oops. Let's go back to the highlight. This one right here. Now that really means y is equal to x plus 6 over 2. that really means y equals, this is like 1, so it's 1/2 x plus 3. And if you notice, that's a form you're more familiar with. 1/2 x plus 3, well, my y-intercept would be right there. Rise 1, run 2, you'd be right there. Rise 1, run 2, so we'd be here, here, rise 1, run 2, we'd be here. So that's that green line. This one down here, now, the y-axis doesn't go down that far, but we'd be down here at -6. The slope would be 2 over 1. So up 2, right 1. Up 2, right 1. And you can see that basically that line would go like that. So that's the blue line. Notice they drew in the line y equals x, which is the reflection line. So these two are inverses of each other. Okay, that's what they would be. If you reflect those lines over that dashed line, they would be inverses of each other. All right. Now we're going to look at verifying, given two functions, okay, two different functions, we're going to see if they're inverses of each other. All you need to do, and this is one method and probably the easiest method that I'll show you, is switch x and y in one equation, solve for y to see if you get the other equation. So what do I mean? I'm going to take a look at this function right here. We've got f of x equals 3/4 x minus 6. Now I'm going to write it as y equals 3/4 x minus 6 because functional notation, that means y. So what you want to do is, what we're going to do is we're going to switch x and y here. We're going to find the inverse of this function basically and see if it's the function g of x. We're going to see if we come up with that. If we don't, they're not inverses of each other. So we're going to make this x. We're going to make this y. So there's what I have. Now we're going to solve for y. So I'm going to add 6. So I have x plus 6 is 3/4 y. Now you got to do a lot with multiplying by the reciprocal here. So I'm going to multiply by 4/3 to cancel out here. So I'm going to take this side and I'm going to multiply by 4/3. Now you need to distribute. So I get 4/3 x plus, now if I do 4/3 times 6, it'd be, if we don't do any reducing right away, it'd be 24 over 3, which is 8. You could reduce first, 4 times 2 on top would be 8, but we get 8 there. So it's y equals 4/3 x plus 8. And notice what we got there is the same as this function g of x, 4/3 x plus 8. So yes, they are inverses. If we solve for y correctly, switch x and y and solve for y, and we don't get the other one, they're not inverses. And that's the easiest way to determine whether or not they are inverses of each other. And that is lesson 7-8.